Hello guys, we will continue examining examples under point 3.2 to get us more used to illustrating problems of particle dynamics into a diagram with applied forces or a free body diagram. Example number 5 states the following. A small pebble of mass 500 grams is attached to the lower end of a light string. So there is a round object of mass 500 grams attached to a light string that we can ignore its mass. Then we sketch this as follows. Here's a pebble or some sort of a round object that is attached to the lower end of the massless string. And here is the fixed ceiling that the string is hanging from. The mass of the pebble is 500 grams, or in metric units, it's 0.5 kilograms. Now, before proceeding with the given, let's determine the forces that act on an object hanging from a string. So let's think about it ourselves. First, there is the gravitational effect of weight that acts downwards perpendicular to the ground as follows. Weight is the mass multiplied by gravitational acceleration g. In this case, it is 0.5 kilograms multiplied by 9.8 meters per second squared. That is equal to 4.9 newtons. On the other side, acting upwards along the string, there is the tension force that counteracts the weight and keeps the pebble hanging from the string. So it holds it up, it pulls up, it connects the pebble with the ceiling and keeps it hanging. Back to the example, we are asked to find the tension in the string in A, B, C, and D, which are 4 different cases. Let's check these cases. In part A, we should find the tension in the string when the pebble is moving upwards with an acceleration of 2 meters per second squared. So here is an upward acceleration with a magnitude of 2 meters per second squared. Then the positive direction along the y-axis is upwards. Next, let's sum the forces along the y-axis, where the summation of forces along the y-axis is equal to ma. Then the summation of forces along the y-axis is plus t, acting upwards and positive, minus w, acting downwards, thus negative. Then plus t minus w is equal to ma. Mass is 0.5 kilograms and acceleration is 2 meters per second squared. Then t minus 4.9, the weight, is equal to 0.5 multiplied by 2, that's equal to 1. Then we move the negative 4.9 to the right side of the equation, and t is thus 4.9 plus 1, that's equal to 5.9 newtons. So the tension is equal to 5.9 newtons. Next, in part B, the pebble, that's our object, is moving downwards with an acceleration of 3 meters per second squared. Then here it is, a downward 3 meters per second squared. This is the acceleration. And the positive direction is thus downwards. Again, the summation of forces along the y-axis is equal to ma. That's Newton's second law. Then what forces are applied along the y-axis? Again, there is the tension acting upwards, opposite to the positive direction, thus negative. There's the weight acting downwards in the positive direction, thus positive. So there it is, we have a negative t plus w, that's equal to 0.5 multiplied by 3. Acceleration this time is 3 meters per second squared. This results in a negative t plus 4.9, that's equal to 1.5. This is the product of 0.5 and 3. Let's move the 1.5 to the left and the negative tension t to the right. Then the equation rearranges into 4.9 plus 1.5, that's equal to t. T then is equal to 6.4 newtons, which is the tension in part B. Let's move forward to part C, where the pebble is moving downwards at a constant speed of 5 meters per second. This is a case of a constant velocity. A constant speed or velocity means zero acceleration. That is, the rate of change of speed or velocity is zero, which is acceleration. Acceleration is zero. Let's approach this by setting the positive direction downwards. Then the summation of forces along the y-axis is ma. Acceleration is zero, then ma is zero. So the summation of forces is equal to zero. Then we have a negative t acting upwards, opposite to the positive direction, thus negative. There is w acting in the positive direction of motion that we set up to be downwards. Then t is simply equal to w, that's equal to 4.9 newtons. This is t in part C, that is equal to 4.9 newtons, the weight of the object. Finally, in part D, the pebble is moving downwards with a deceleration of 4 meters per second squared. Deceleration is a decreasing rate of speed. It is a negative acceleration. So we assign its vector, however, in calculations, its value is negative. Then here is our deceleration downwards, but with a negative value, a negative magnitude, that is negative 4 meters per second squared. The positive direction along the y-axis is downwards. So motion is downwards, but with a decreasing speed or velocity, thus a negative acceleration or a deceleration. Alright, then the summation of forces along the y-axis is ma, mass is 0.5, acceleration a is negative 4. Then the forces are as follows: weight in the positive direction plus w minus t, that is opposite to the positive direction, and this is equal to negative 2. It's negative 4 multiplied by 0.5. Then weight is 4.9 newtons, and there is the negative t, and 4.9 minus t is equal to negative 2. So we move the negative 2 to the left and negative t to the right. Then 4.9 plus 2 is equal to t. Thus, t is equal to 6.9 newtons. So this example problem was simplified once we prepared a proper drawing of the diagram of the particle and the applied forces. Then we assigned the acceleration as per each part in A, B, C, and D. And we assign the positive direction along the axis of acceleration, or along the velocity, or applied forces. Then we simply use the equation of Newton's second law, which is the summation of forces applied on a particle is equal to the mass multiplied by its acceleration, to calculate the unknown tension force T.